organizers for giving me an opportunity to give my recent research. So I actually really like this conference. I'm really stimulated by with interesting discussions here. Okay, so I'll talk about some theoretical studies on about the origins of late-time radio emission in tidal disruption events. But I believe most of the people already know one of my models, some off-axis model, EJET model, but I try to recap the concept. And the other half of my talk, I will also, I would like to present my recent model. Actually, the paper is already up here, today's archive. Okay, so before going to the details of the late-time radio emission, maybe it's still helpful to talk about what we can learn from radio emission in TDEs. So this is some radio light curve, and already, you know, the synchrotron, they are mostly, they are produced by synchrotron emission, and we can learn the nature of outflow or environment surrounding the supermassive black hole. And some relatively low luminous radio flares, they are produced by Newtonian outflows. And so this is a typical analysis we are doing for radio flares. So the situation is like this. Some tidal disruption event happened, and it produced some outflow. I don't know the mechanism to launch outflows, but now I'm just assuming outflow is launching. And then it collided with the medium surrounding the supermassive black hole, and it make a shock. Then at the shock front, the electrons are accelerated to the non-relativistic energy, and also magnetic field is amplified. So in this situation, we can reasonably assume, we can believe some synchrotron emission happens, and we will see some radio flares. And typically, this is a spectrum. So spectrum has a peak, so this is produced by synchrotron self-absorption. And we have two quantities. So this is a peak frequency and the peak flux. So we have two of the quantities, and actually we can write down three equations. So this is a peak frequency, this is gyro frequency boosted by relativistic effect. So by identifying peak frequency, we know we can constrain this quantity, the combination of these quantities. And also, you see, this component comes from optically thin synchrotron emission. So, of course, in this case, the luminosity, flux is given by synchrotron emissivity of single particle times the number of total particles. So by, by using peak flux, we can constrain this quantity, the total number of emitting particles times magnetic field. And also this part, the lower frequency part, this is optically thick. So we can use some Rayleigh spectrum. And actually this part gives us the constraint on the Lorentz factor gamma times the surface area of the emitting outflow. But here we have four unknown quantities, the magnetic field and the Lorentz factor of emitting electron and the size of the outflow, and also total number of electrons. So usually we cannot solve these equations because we don't have, we need another equation. But fortunately, we can construct this quantity. This is magnetic field energy and the non-thermal energy of non-thermal particles, and they are already Buzz explained this. We see this energy is actually depends on the radius very sensitively. So this is some schematic picture of total energy. So if you remove, and there is some characteristic radius which minimizes the total energy. And if you leave this radius just a little, then the required energy becomes much, much larger. So practically, the radius of the outflow is constrained in this equipartition radius. Then now we know what is the location of the outflow, so we can calculate what is the Lorentz factor gamma and magnetic field and the total number of particles. So this is some typical analysis. And for example, this is a 2090 DSG. So you see time evolution of radio spectrum, and we know where the location of peak flux peak frequency and peak flux. And by applying this analysis at each time of the spectrum, we know the evolution of radius, and also we can reconstruct the density profile surrounding the supermassive black hole. Okay, so this is very, I like this analysis, very beautiful, yeah, theoretically very beautiful. And for very, very bright radio emission, we believe maybe this radio emission is produced by relativistic outflow. And in this case, the situation is like this. We have additional degree of freedom, so Lorentz factor gamma. And in this case, we have to take into account relativistic effect, and some equations are modified. But now we use additional equation. So basically we can do the same analysis as Newtonian case, and we can get what is the Lorentz factor of gamma or some other quantities. So basically we obtain, actually in this case, Lorentz factor is larger than unity, so the outflow should be relativistic. Okay, so this is some basic story. And so this is a recent discovery of late-time radio flare. And some people started to discuss maybe outflow was launched at late time. So maybe this formation happened at late time, about 100 or 1,000 days after the optical discovery. But I would like to consider about this scenario of axis jet. But unfortunately, maybe you know already this scenario, how this scenario works. So this is what I did in this paper. So when we are observing relativistic outflow from different viewing angles, of axis, then additional free parameter appears. So in this case, the Lorentz, we have to replace relativistic Lorentz factor gamma with relativistic Doppler factor delta. But the analysis is basically the same. And what we found is another new radius appears, and we have actually two minimizing radii corresponding to on-axis and off-axis solutions. So this allows us to interpret the observed radio flare could be produced by off-axis outflow. Okay. But maybe some smoking gun could be obtained by VLBI observation. So in our model, this HYZ, the radio flare HYZ, is produced by relativistic jet expanding in the perpendicular direction from our line of sight. So our expectation is in light curve, maybe at some point the deceleration happens, and this light curve has a peak and join this jetted TD light curve. And if we observe this object by using VLBI, maybe we should detect some point source moving at the speed of light. See? So I'm looking forward to see the future VLBI observation. Okay. So, however, the story is more like complicated. The late-time radio flare is more ubiquitous. So about 40% of optical TDEs show very late-time radio flares at about 1,000 days after the optical discovery. So, but on the other hand, we know what is the event rate of relativistic jetted TDEs. This is on-axis jet TDEs. The event rate is about 10,000 times smaller than the optical or X-ray TDEs. So even if we take into account the beaming factor, beaming effect, about maybe 100, then, but still, the off-axis jet TDE event rate should be 100 times smaller than typical optical TDEs. So off-axis jet TDE is not ubiquitous. So it is very problematic. So today I will talk about some new model to explain this late-time radio flares without adopting any relativistic jet. So my main focus is these two events. So 2019 DSG and 2020 VWL. So they show double peak light curve. So this is very interesting. And I would emphasize that after the first peak, this light curve, this is light curve at 6 gigahertz, but in this frequency, the light curve, spectrum is already optically thin, okay? So then this means the mechanism to produce first peak is transition from optically thick to optically thin. But in this case, yeah, this time variation is produced by different mechanism. So here I'm showing again the flux of optically thin synchrotron flux, and this is related to two factors. And now I'm focusing on this factor, total number of electrons. This could be estimated by the number of surrounding number density of surrounding medium times the volume of the outflow. So maybe I guess something happened in either of these quantities. Okay. So the basic idea, okay, so then my model is, the idea is very simple. So let's consider about what will happen when the outflow is expanding long time scale, about 1,000 days, with the 10% of the speed of light. Then the radius is about 10 to the 17 centimeter. And interestingly, this radius is consistent, comparable to the bond radius of the supermassive black hole. Here I'm showing the bond radius corresponding to the million solar mass black hole. And maybe someone think maybe I'm using some strange temperature, but actually this temperature is motivated by observation of our galactic center. So Chandra detected diffuse X-ray emission around the Sagittarius star. And and this diffuse X-ray emission is explained by Bremsstrahlung and KEB temperature. And also nearby galactic center, Chandra also detected diffuse X-ray. So the temperature should be 10 to the 7 Kelvin. Okay, here I'm writing down some schematic pictures, some density profile. And at this bond radius, the density profile, flattening. So outside of this radius, particle or some gas does not care about the gravity of a supermassive black hole. Okay? So then outflow is expanding and it arrives at this bond radius, then the number of particles swept up by blast wave is increasing as time goes. So it may naturally produce some second flare. So as a proof of concept, I calculated the radial light curve at 6 gigahertz. I'm using some forward modeling. I'm adopting some very simple outflow model. The mass is about 0.1 solar mass and expanding about 0.1 C. And this is some synchrotron microphysics parameter. And expanding inside of the bond radius, the density profile is R to the minus 2.5. And naturally, some of this double peak light curve is produced. The reason is, and the first peak is produced by optically thick to thin transition. This is the same as the previous radio flares. And when the outflow arrives at the bond radius, the light curve has a minimum. Then the outflow is expanding larger and larger, but at some point, the swept up materials, the mass of swept up materials, it becomes comparable to the original mass of the outflow. Okay, so it starts to decelerate, and light curve start to decline. So this mechanism to make this is the same as a binary neutron star merger, kilonova afterglow or radio supernovae. So before going to fitting actual observed event, I try to explain the parameter dependence of this model. So here I'm just changing the slope of the density profile. So interestingly, if I decrease the slope, then this first peak disappears. So this is mainly because the material inside the bond radius is, the density inside the bond radius is getting smaller and smaller. And this maybe explains some diversity in the radial light curve observed for example, 19 HZH. And to have this very slow rise light curve, the density slope is about 1.5. This is consistent with Bondi accretion. So maybe black hole, supermassive black hole accreting in bond accretion happens, maybe we detect this very slowly rising light cloud, radio flare. So I'm changing here the number of ISM density and the ejecta mass. So it controls the deceleration time scale. You see some deceleration happens. So yeah, this is basically as I explained the same mechanism, the radial peak in binary neutron star mergers. Okay, then now I turn to fit actual observed events. But I would say that I did not carry out some serious fitting process. So this is not the best fit parameter. I just changed the parameter values from the typical numbers and try just check this model works. So basically, I'm demonstrating the potential of this model. So for these two events, right curve may be reasonably reproduced by this model. And for the other event, the data is maybe not sufficient, so maybe I can do anything. But maybe it could be possible. So, and this is the last part. Now 5 minutes. Okay. So then the most interesting part of this model is, so we can estimate the mass of supermassive black hole. Why? Because this minimum tells us the location of bond radius. Okay, the bond radius is proportional to the mass of supermassive black hole, but there's some uncertainty of the temperature of the ISM gas. But let's assume the temperature is around the KV. Then, by identifying the minimum location of the minimum, then we know where is what is the mass of the supermassive black hole. Okay, so here I'm showing this is the minimum time scale of minimum and the luminosity, and here I'm showing the location of each observed object. And I'm recasting, converting the quantities. So x-axis is bond radius, and y-axis is ISM density. So, and assuming this relation bond radius is proportional to the black hole mass, then the suggested value of supermassive black hole mass is about 1 million solar mass. So this could be consistent with other values suggested by other observation. And also, we can also learn the energetics or mass of outflow producing radio emission by detecting second peak. So we should detect second peak because most of the radio flare is still rising, but at some point it has a peak. So now we have just lower limit of this luminosity and time scale of peak. But I'm recasting this relation to the ejecta mass and the density, ISM density. So here my calculation suggests I can get only lower value of the ejecta mass. And this is about, only lower limit, but in the future by detecting second peak, maybe we can, we know what is the origin of outflow. Okay, this is my summary. So the most important part is my recent model. So just by using single outflow, then we can produce double peak light cloud, and it can tell us black hole mass and outflow mass and energy. Okay, that's it. Thank you very much.
Okay, any questions?
Okay, I'm the first one. So you have your boundary radius, you have your density, and you have your sound speed. What is your boundary rate? What's the accretion rate?
Boundary rate is about 0.1% of Eddington.
Oh, then it's very faint.
So still lower than the accretion rate of low luminosity region.
I see. Yeah, so these ones, then those are too faint, perhaps, to see much. But it would be interesting to see if there's any AGN activity, what kind of, maybe these are too faint. I don't think they produce too much of emission for us to see.
But this is consistent with the current, criterion to select TDEs, right?
Yeah, these are non-AGN, no bright AGN.
Hi. So we have a lot to discuss, I think, but just really quickly, so for all the TDs that you have some where it's like, okay, the second pump you'd see, even if you don't see prompt emission, radio emission, but for basically then in all the cases where you have prompt radio emission, will you eventually see a second bump? Is that what you're saying?
Mm-hmm. Yeah.
Okay, so we just have to keep waiting and keep looking.
Yes, yeah.
Yeah, so about the assumption on the temperature coming from observation of the galactic center. So does that resolve the boundary radius?
Yes, absolutely, yeah, resolved.
Okay. And is it correct that the uncertainty in the temperature propagate to the mass as temperature squared? Like fixed boundary radius, basically.
Not squared, just inversely proportional to the.
I mean, into the estimate of the mass.
Yes.
But you're saying just linear.
Linear, yeah, linear.
Okay, sorry. Thank you.
Hi, Tatsuya. I really like this idea of complicated CNM. I just had a comment that with my student Alexei and his PhD, we tried to do more detailed models for the density profiles where we included the energy injection from the stars and the mass from the stars. And we, in general, could get two breaks. There was a break at the stagnation radius, and there was a break at the Bondi radius, which is, separated influence. Of course, it depends on the age of the stellar population. Like in the galactic center, you just have a bunch of young stars that are dominating the M dot, but in other environments, you can have old stars. And my point is just there could actually be two breaks in principle. Is the comment? So
okay, that's interesting.
So if we see 3 bumps, you have a model already ready to.
Yeah, but actually the boundary radius in this figure, in this estimate, is consistent with stagnation radius in your work because this is controlled by the temperature of the, shocked stellar wind, right?
Right.
And in the case of our galactic center, this temperature is actually explained.
In the galactic center case, they're the same. It's just in general, it can be more common.
Yes.
So I guess a comment and a question. So in the galactic center, and in fact, I think in all systems where we have data, the density profile is not constant outside the Bondi radius. In the galactic center, it actually falls as 1 over r squared because it's a freely expanding wind. The stellar winds that are not captured by the black hole just expand out of the galactic center. So how sensitive is your model to whether the density is actually flat outside the Bondi radius or you just have a mild break in the density profile?
Then in this case, we cannot get very, very steeply rising light curve. The light curve becomes more shallower. So it may be a problem because most of the late-time radio flare is increasing very rapidly.
Yeah, it's hard to in galaxy clusters as well. When you look outside the Bondi radius, it's not exactly a constant density medium. It's still a decreasing density.
But maybe it depends on some distribution of the stars surrounding the, I don't know.
Yes, that's fair.
And a more interesting point is if some feedback happens, supermassive black hole has some feedback, then maybe density, density profile could be increased. I don't know, maybe this is a kind of potential explanation why some TD radio flares are increasing more very rapidly.
Okay, any other questions? All right, let's thank Tatsuya again.